here. I'll try to download it and upload it to YouTube, so you can find it on the YouTube channel as the other tutorial emails. So this is the revision copy. I'm not going to do this one now. I'm going to do the week number 5 first, then we're going to go back to the week number 6, and we're going to start with our questions. So it's not going to be a presentation format. It's just going to be about, okay, now that the situation we have. I think there was a question similar to this one. We have the 15-kilogram rod is pinned at the end A, and it's going to be released downward. The omega was given as 5 radian per second when it's going to be in horizontal position, as we can see here. So obviously we have the length, we have the mass, and we can calculate the IG. And from there we have the both the angular and the angular acceleration and the angular velocity. And we are going to have, in that case, both the angular acceleration, linear acceleration, and the angular normal acceleration. So the solution for this one was done that way. We are going to say that the sigma of the moment around the A is going to be equal to the I multiplied by alpha. That's what we have in the free body diagram, and that's what we have in the kinetic diagram. Well, just to remind me, this quiz is covering the week 4 and 5 or 5 and 6? Yes? Is it 4 and
So
5
I
or 5
I
and
think
6?
it's 4 and 5. So that's what I was
Okay.
asking you. Is it 5 or 6 or 4 or 5?
I'm asking you now. Anyway, I'm too lazy to go to Dongbin document and check that, but you forced me to do that. So let's go back to my Teams, and I will go to Dr. Dongbin. He sent me a document a few days ago about what and which, and I'm going to show you this one here. Okay, so you have that, of course, the plan, the teaching plan we have for the subject. So now we are in the week 5 quiz. We are in week 7, right? So yeah, so this will be about the kinetic equations of the motion process and work and the energy process. Oh yeah, so yeah. So this one is going to be mainly about the week 4 and 5. And the next one, general of the motion. Yep, kinetic equations of the motion. And this one is going to be the next 2 weeks, 6 and 7. Okay, yep. So we're going to cover 4 and 5. This is the 5 now. And I think that we already have similar questions going to show up in the quiz. This is the easiest one. The most important thing is the schedule free body diagram and the kinetic diagram. You can see that in the free body diagram, we're going to put the location of the reactions at the point A, and the weight is going to be in the centroid downward. In the kinetic diagram, we're going to have where are going to be the forces going to be effect to make a motion. So here we have the mass multiplied by the acceleration y, and this is the mass to the acceleration x, and this is the alpha and the omega, which is going to go either ways. We don't know exactly. We know the omega is going to the clockwise direction. So now that's it. We only have to apply the 3 equations saying that whatever the forces we have in the free body diagram is going to be equal to the forces we have in the kinetic diagram. And thus we are going to say that for example, to the x-axis, the ax is equal to the magx. Well, the magx is going to be the normal acceleration, which is the omega multiplied by the distance from A to G, omega squared multiplied by the distance A to G. Then we can find, for example, what will be the velocity here, because we know the omega. For the y direction, we're going to have the ay positive, the w negative in the free body diagram. On this side, we're going to have the m multiplied by the agy, and we're going to consider that to be negative at the beginning. And this will, by solving this one, we're going to find out what the value of the ay in terms of alpha, because we don't know what the alpha is. To find the alpha, we're going to do the moment around the point A, and in that case, going to be equal to the IG alpha in general. But here, Also, we're going to have that this mass to be multiplied by that distance. Oh, sorry, this force multiplied by the distance AG. So, of course, the IG for this bar is going to be 1/12 multiplied by its length square multiplied by its mass. Okay, and this side, the weight is going to do the moment and is going to be clockwise, so it's going to be negative. This one is also going to be negative, and this will give me the value for the alpha, because the alpha is going to be the only unknown we have. Yeah, you have a similar question in the quiz. I noticed that earlier. Okay, so maybe I done it in a different way. You can see that that's the solution they have, but I made it a little bit easier by taking, oh, sorry, no, they were taking the moment around the point O, and I changed it to be around the point A. And with this one, we found the answer is going to be quite simple. We find the alpha, then we can find the AY, because the AY has been calculated in the terms of alpha, as you can see here. Now you have this question. You can go back to it if you have a similar question in the quiz. That's for the box that's actually going to have the part to be removed from here. Again, we did some changes. I didn't take the acceleration about the point G, and instead of that, I take it around the point A to simplify the calculation, because around the point A, I'm going to eliminate the forces at the point A, which is one of them is going to be unknown because we don't know what the alpha is. Now, anyway, the trick in these questions are going to be how to find the acceleration that's related to the omega, to the alpha and the omega, which is the normal and the tangential one. So here I just sketched this slide to show you how we're going to do the process. Find your link. Find the link of the rotation, and then you can simply locate where we're going to have the acceleration, the normal and the tangential. So this is tangential 1, which is going to be related mainly to the alpha. This one is going to be equal to the alpha multiplied by the length of the red. Again, let me change the color of this one. By the length of the red link. For the normal one, is going to have that direction. Yeah. Okay, I'm going to leave it in blue. And that will be related to the omega. Omega squared multiplied by the length of the red line. Okay, so here we said, as long as we're going to say something like starting from the rest, okay, or just simply removed from the rest, that means that the omega is going to be equal to 0. Then I only going to have the alpha to do the work. And then I can write down that this acceleration is going to be equal to the alpha multiplied by the length from G to A. And of course, this acceleration can be divided into two components, which is going to be the X component and the Y component. Simply, if I know what the value of the angle of the acceleration in general, if I know this angle or that angle, I can multiply that by the cosine and the sine, and I will get the value. Usually downwards, we're going to consider it as negative. To the left, we consider it as negative. Otherwise, it's going to be positive. Now we have the free body diagram and we have the kinetic diagram. Well, actually, I put that in the free body diagram, which is wrong. This should be done on the kinetic diagram. Okay, and here we have the weight going downward to reaction at the point A, vertical and horizontal. And now on the kinetic diagram, we're going to have the mass multiplied by the acceleration that we found here, which is alpha multiplied by the R. And we're going to find the value for the alpha. So again, we calculate the value for the IG and apply the three equations, and we came out with the answer for it. So we start with the listing of your known and the unknown. Even we're going to do that on the paper before you are going to upload it. You need to do that. It's going to be for your own benefit. Now we do the forces about the point around the x-axis. So we had the ax, and we're going to have the ag multiplied by the cosine of theta multiplied by the mass. That's what we're going to have on the x-axis. On the y-axis, it's going to be the ay minus a w, and this one is going to be on the other side to be a negative of the mass multiplied by the ag ty. And then we can solve for that. First, we calculated the IG, calculated normal and the tangential accelerations. We found that this one is 0 because the omega-1 is equal to 0. This one is going to be 0.282 alpha because we know that the R from the point G to the A is equal to 0.282 meters. The alpha is unknown. Now, if I can take it to the x direction, I need to multiply it by the sine of 45 degree. So I can take it to the y direction, I get to multiply it by the cosine of 45 degree, and I set up the value for the acceleration to the x and the y. And that's it. Forces to the x-axis, forces to the y-axis. We're going to find both reactions in terms of the alpha. Then I need to solve for the alpha. So I will do the accelerations, the moments around the point A or G. This is doing through the point G. I find that this one actually is going to be quite complicated. So I done the moment around the point A, which is going to make it much easier for me to find the answer, because as I told you once again, I'm canceling the AX and the AY and using with the weight only. So you can see that that's what we have on the free body diagram instead of that. Okay, and that's it. I just applied that and I got the answer directly for the alpha. And then I substitute in the equation 1 and 2 to find the value for the reaction AX and reaction AY. That was the other question, which is not much different. The most important thing is going to be the trick to sketch the free body diagram and the kinetic diagram. So you can hear for this spatula, this is the reaction forces we have. We have a friction force and we have the normal force. For this example, the theta starts from 0 and is going to reach 30. So we need to do some interpolation. And we're going to show you actually what the relation we're going to have between the omega and the theta and the alpha. Okay, so we start with the free body diagram and the kinetic diagram. Once again, we have a normal and this is tangential acceleration, and this is normal acceleration. We don't know what the omega is in the second state, and we don't know what the alpha is in the second state. So we did once again, I just resketched them by hand, and then I defined the equation we're going to use, define the parameters given to us, and start to apply the equations. So first I started with finding the accelerations in the normal and tangential directions, calculated the IG because we know the mass and we know the rates of gyration, and we take this acceleration to the x and the y direction because this will make it much easier for us to match them with the friction force and the normal force. So we found the AGX and the AGY by simply change the normal and tangential acceleration into these two axes. Now we got this value. We're going to do the sigma of the moment forces to the x, to the y, and the both the free body diagram and the kinetic diagram. So we got some relation between them. Actually, we can solve, of course, for this one and get the answer because we have sine, we have cosine, and then we can find the equation to be finalized to be in terms of the alpha and the omega. Again, we found that actually the moment around the point G is going to be impossible to be done because we're going to have three unknowns in these equations, and this will make it very hard to be solved. You can see that we have the F, we have the NA, and we have the alpha. So this is usually not going to be recommended. So we did the moment around the point A instead here, okay? And we can simply do the calculation, and we simplify it to find the value for the alpha, because only one unknown is going to be shown here, which is the alpha. Okay, because the moment AGT is the alpha multiplied by the R. So we can solve for the alpha. So now how we got this value here, 3.19 sine of theta, because we just divided this value by the sine of 30 degree, which is the recent value for the theta. Okay, so we got the answer to be 3.19, and we put sine of the theta. That means the alpha, when the theta is going to be 15, is 3.19 sine of 15, and so on. Now we know that the alpha changing with the theta is going to be the same value of the omega multiplied by during the time. So we got this equation. The alpha now is equal to 3.19 sine theta. So we can replace that here. And we did the integration for both sides. That's changing from 0 to 30. This one changing from 0 to the omega 2. And then we can find the value of the omega 2. And then we can apply it to the equation 1 and 2. We can find the friction force and the normal force. And dividing the normal force by the friction force, friction force by normal force, we can find the coefficient of friction. Okay, that's alternative method I used, which is not much different, but in all the cases, we just find the value for the alpha, then we continue doing the same way. So that was the question for the week 5. Let's go back to the week 4. Let me get the slide from my OneDrive, week 4. So the week 4 actually is not much different from week 5, except that we didn't include the accelerations and the forces. Yes, this something, there are something similar to this one when we need to calculate, for example, the acceleration and other stuff. Wait a second, I remember that I saw something similar to the guy who was pushing the bar that we covered in the week 6, which is this scenario. I found something similar to that. Okay, so yep, it's going to be worth actually to cover the week 6 as well. So let's cover the week 4 first, then we're going to come to this one. Again, what you can see here that we're not going to have any relation to the omega and the alpha. The thing is just going straight forward. So that's why, well, linearly. So we're going to make a relation between the free body diagram and the kinetic diagram. In this scenario, the part is sliding. So we are going to have need to find what will be the reaction here. So in the free body diagram, we're going to have the AY and the AX at the point A. The free body diagram is going to have this, the mass of the bar multiplied by this acceleration. That's it. Now we're going to say that the sigma of the forces to the x-axis are equal to 0, which is going to be equal to the ax on this side, equal to the mass multiplied by the acceleration a, multiplied by the component, by the sine of the, whatever, by the sine of the cosine of the angle that will make it horizontal. Okay, and the same thing for the y direction. The ay minus the w, that's the vertical component, is going to be equal to the vertical component of the mass multiplied by the acceleration a. Finally, if I would like to know what the other parameters like, I can use the moment as a third equation. So I can say that the moment around the point A on the free body diagram was going to be equal to, now what do we have? We don't have any actual component to that. So we can calculate the moment is going to be equal to the mass multiplied by the acceleration multiplied by this. Or you can use the horizontal component of the MAA multiplied by the distance from the center to the end A. So you can see that's what we've done here. We're going to use the IG value, of course. The acceleration can have the acceleration x component and acceleration y component, and we're going to come to the equation here. So you can see the three equations are the forces to the x-axis is equal to the mass multiplied by the acceleration component to the x. To the y-axis is going to be the mass multiplied by the acceleration to the y-axis. And the moment around the point A is going in the free body diagram is equal to the moment to the kinetic diagram. So we just applied that. We didn't employ the IG because there's no rotation. I think I gave you an example on that in the class yesterday. If I'm going to throw the pen in the air, it's going to come down. It's going to come down just horizontal or just vertical. Then I don't have any rotational components. So no omega is going to be involved, no alpha is going to be involved, and of course no IG is going to be involved. But if the pen is rotating during its movement, so I need to use the IG, the alpha, and the omega because we're going to have different components for the acceleration. That's question. I saw many examples similar to it in the quiz and in the end of the chapter questions. We're not going to cover this one here because we're going to cover it somewhere else. In all the cases, we're going to have the three relations of the forces to the x, forces to the y, and the moment. I hate this person with the noise. Anyway, I don't know him, but I hate the noise he's making. Okay, so yes, I will prefer to go to this example because it's a four-bar mechanism. Three links are rotating around the point A with the certain value of the omega and unknown alpha. We need to know what the alpha is. So we're going to take the box itself. We're going to make the analysis for that. You can see that we're going to have the weight going downward and the weight is going downward, and we're going to have friction force and normal force. Usually the relation between the normal force and the friction force is that the friction force is equal to the coefficient of friction multiplied by the normal force. In the static situation, the normal force is equal to the weight, but if we're going to have movement, there will be differences. So this is a free body diagram, and this is the kinetic diagram. We're going to have the mass multiplied by the acceleration in the x and the y. How we can find these accelerations? We need to go to the free body diagram, and simply we are going to have the link AB is going to have two components of the acceleration, normal and tangential one. So that will be the normal, that will be tangential, which is going to be related to the alpha, and that will be the normal, that's going to be related to the omega. So this one is alpha multiplied by the r, and this one is going to be equal to the omega squared multiplied by the r. When we say r, it's the distance from the A to B. Done. Okay, so when we're going to have the acceleration at this point is going to be the acceleration on any other point along this link. And we learned that from the week number 3, I think. So now that means that the horizontal force here is going to be equal to the mass multiplied by this acceleration, which is tangential 1, or the alpha multiplied by the length of the bar AB. And for the downward one is going to be equal to the mass multiplied by the acceleration normal, which is going to be equal to the omega squared multiplied by the r. So the omega squared is 4 multiplied by 1.5 is going to be 6. Now, once again, I only going to take the sigma of the forces to the x-axis is going to be 0.4 MB, and this will be equal to 10 multiplied by 1.5 alpha. To the y-axis is going to be the MB minus the 98.1, and this will be equal to negative 60 on the other side. And then we can take the moment as well and do the solution. Well, yeah, we don't need to actually take the moment here because we have two unknowns, so we're going to have two equations to do that. So from the normal forces or the upward one, we're going to have the value for the MB, and for the horizontal one, we can find the value for the alpha. We need to do this one first, so we can substitute in the the normal forces, the vertical forces, and we can find the answer for the alpha. Okay, so once again, this the process. You can find the video for this one available for you in the same channel. Now that's a box which is going to be lefted. I don't know if I saw something similar to that. Well, I saw something similar to this one. Well, the requirement was different. You need to find the acceleration, not finding the, here we need to know what is the, what you need to find here. Oh, he want to find the reactions. And the other question, you need to find the acceleration. Anyway, the concept is going to be the same. If you sketch the free body diagram, then everything will be okay with you. Now let's go back to the question that I prepared. Again, this one is just recent one, so you can find all these tutorials. Mainly this one, I saw 2 questions similar to that one. Okay, so oh, this one, the same one exactly was in the quiz, and not this one specifically, but if you understand this one, everything else is going to be easy to be done. So now let's go to the revision session, and the first question is going to be about a trolley pushing a carrot, and this carrot is actually inclined, so it will try to slip, but we don't know actually if it's slipping or not. So we have the uniform crate. It has a mass of 50 kilogram, okay, and rests on the cart having the inclined surface. They remind the smallest acceleration that will cause the cart either to tip or slip relative to the cart. What is the magnitude of this acceleration? What will be the, well, we know that the coefficient of the friction given to us to be equal to 0.5. So the first thing we have to do if you're going to have such a question is sketch a free body diagram. So this is my free body diagram. Obviously, you can see that the normal force is going to be normal to the surface. Well, let me get my pointer. So the normal force should be normal to that surface, the bottom of the box, upward. What are the messages I have? Just give me 1 second. Maybe people try to get to here. What is the emails? Okay, I don't know actually what the message I'm receiving, but I'm receiving messages. Anyway, that doesn't matter. Okay, so yeah, and the friction force is going to be parallel to that surface. And that's what we can explain in the free body diagram. The mass is going to be at the center here going downward. Now, typically we don't have any rotation in this scenario, so we don't need to find the IG or the omega or whatever thing is. We're going to just keep it as simple as we can. So I start to become curious to know actually why I'm receiving too many notifications. So I'll check the email here to see what's happened. That's not your email. It's the no, it's just something like a weekly newsletters. So don't worry about that. It's not about you. Okay. Now once again, yep, we're going to have the mass going downward. It's going to be 50 multiplied by 9.81, and it's going to be inclined by the 15 degree, which is the angle of the inclination for the box itself. And here we're going to have the friction force parallel to the inclined surface, and this will be normal force, which is perpendicular to that surface. Now, because we have the acceleration is going to be horizontal, we can choose whatever the axis we will use. So you can either take the x-axis to be that one and the y-axis to be this one, or you can simplify it to use that this is the x-axis and this will be the y-axis. Well, once again, it's going to depend on how you want to do it. Okay, because for example, in the point where we're going to calculate the moment, the weight is going to be acting on this small distance here. Okay, so maybe, I'm not sure, but maybe this will be something that may confuse you in the calculation. We will see that. Okay, so this is the kinetic diagram, the mass multiplied by the acceleration A. We take it to this direction because the force is pulling the carrot. And that will be distance x that we don't know how much, and we need to find the value for this x. The height from the A to G is equal to 0.5, which is the half of the height we have for that box. Okay, so we didn't take the things to be in the middle. We want to know exactly where will be the point A location. Now, these are the three main equations we're going to use. We use this one because there's no rotational for the part. It's just still fixed, moving linearly. So there will be no omega, no alpha, no IG. So now we start to do the analysis for the forces. First, we start with the case of doing the analysis to the tangential and the normal. Well, actually, this should be x and y. Anyway, obviously that they use this one to be the x-axis, and we call the x-axis prime, and this is the y-axis prime. So you start with the ay prime is equal to the mass multiplied by the acceleration gy. I did the moment first, but I don't know where's the equation for the moment. Anyway, the moment in the free body diagram is going to be equal to the moments in the kinetic diagram. So from here, what are the moments we're going to have around the point A? First is going to be this force to be in that direction, and then multiplied by the x. Okay, so the weight to be on the new y-axis and multiply by the distance x. That's what we have in the free body diagram. Okay, and also we're going to have its horizontal component, which is going to be that way, is going to be multiplied by 0.5 and cause a moment around the point A. Okay, so just let me repeat that. Now, this is the weight. That's the point G. That's the point A. The distance from here to here is equal to x. Distance from here to here is equal to 0.5. Thus, if I would like to find the moment around the point A, simply I'm going to do the following. I will choose this is my y prime axis, and this is my x prime axis. Thus, that's theta, which is 15 in this question. This force, let me change the color of the pen now, is going to have first this component going downward. So define the moment according to this direction. I'm going to multiply the weight by the cosine of the theta, and then multiply by distance x. And this will take it to the clockwise direction. The other component is going to be this force, which is going to be the W multiplied by the sine. And you can see that the direction of the moment that's going to be caused is going to be to the clockwise direction, so it's going to be negative. So sorry, this one is going to do it as counterclockwise, positive, and this one to the clockwise, so it should be negative. And that's why it's going to be the weight multiplied by the sine of 15 multiplied by 0.5, which is that distance. Now let's look at the kinetic diagram. The force 50 times acceleration, again, can be analyzed into a horizontal component and vertical component. The vertical one will cause to the counterclockwise moment, while the horizontal one will cause it, well, actually, I'm also going to do it as counterclockwise. So we're going to write down the other side to have these directions. Still, the x is going to be unknown on both sides. So this will be my equation one. I can solve it to say that the x is equal to, we don't know what the acceleration is. And sorry, the acceleration is given to us, right? Oh no, the acceleration is unknown and the x are unknown. So we can have two unknowns in this equation. So to solve that, we're going to do the forces to the y direction. Now I need to clean that so we can see clear for these forces. So once again, we said that this will be my y prime, and this will be my x prime. So in this direction, we're going to have the first force we know is that 0.5 n. It's not 0.5 in Newton. It's 0.5 multiplied by the n, with the coefficient of friction multiplied by the normal force. So this will be negative, okay, in the x direction. And the weight multiplied by the sine of theta will be the positive components. That's what we have in here. And the free-body diagram. In the kinetic diagram, we have the negative of 50a multiplied by the cosine of 15. In the y direction, we're going to have the weight is going to be multiplied by the cosine of 15 is a negative part, while the n is going to be a positive part in the free-body diagram. In the kinetic diagram, the negative component is going to be the 50a multiplied by the sine of 15. So we're going to find that's equation for the y. The n is positive. The weight component to the y prime direction is going to be negative. On the other side, we're going to have negative of the mass multiplied by the acceleration multiplied by the sine of 15. Now, the only unknown we have in this equation is the n, so I can solve for that directly and find the answer. Now, for the x-axis, we're going to have the friction force, negative, and we have the 50 multiplied by 981 multiplied by the sine of 15, as we explained earlier. On the kinetic diagram, it's going to be the horizontal value for this one, negative 50a cosine of 15. I'm sorry, here we still have two unknowns. Now we have these two equations have two unknowns, so I can find the n as a function of a from the equation 2. Substituting in the equation 3, I can find the n and I can find the a accordingly. Remember that this f is equal to the n multiplied by 0.5. So we can solve for 1, 2, and 3 equations, and we will come to the answer that the n will be 447.8 Newton. For the x is going to be 0.25 meters, and for the alpha is equal to, the acceleration is going to be 2.01 meter per second square. And simply because the x is going to be less than 0.3, which is the middle of the box, that means the crate will not going to be simply tripped, but it will slip. So you may have similar question. I saw something similar to this one, and also there is something similar to that one. We did that in the class over the past 2 days, which is about we have a uniform bar of the mass m is pin connected to the collar at the point A, which slides along the smooth horizontal road. If the collar given as constant acceleration a, determine what will be the bar inclination theta and neglect the collar mass. So to understand that, we're going to have reactions first at the A. We're going to have the acceleration, the AY, and we're going to have the AX. And also we're going to have the mass to be multiplied by the acceleration A, because we're going to have movement. So of course, the mass multiplied by the acceleration A is going to be only in the kinetic diagram. Again, if you take a look to my pen, if I get to throw it or move it horizontally, the acceleration at any point is going to be the same. That means that the acceleration at the point A, which is A acceleration, is going to be the same acceleration at any point we have along that bar, including the one we have at the center. So here we can have that the force equal to the MA as normal. So let's sketch the free body diagram first. and the kinetic diagram. So in the free body diagram, we're going to have the two reactions at the point A, AX, and the AY. The mg, which is the weight, is concentrating in the centroid. The kinetic diagram, the only things moving is going to be the bar point A, and this will cause that we have the force at the centroid in the kinetic diagram is going to be equal to the mass multiplied by the acceleration. So here I only have, we just need to know what the relation of the mass and g and the mass and the acceleration. To do that, we can only use one of the relation, which is going to be the moment around the point A. And in that case, we're going to find the moment around the point A in the free body diagram, and then the moment to the kinetic diagram around the point A. I would like you to actually do that. You can see that around the point A in the free body diagram is going to be equal to the mg multiplied by that distance. But that distance simply can be found by having the L divided by 2. That distance is L divided by 2. Okay, to take this one to here, we need to multiply by the sine of theta. On the other side, or the equation is going to be this one, the mg sine theta multiplied by the L divided by 2. Now, on the other side, I need to find that distance, which is going to be equal to the L divided by 2 multiplied by the cosine of theta. That's it. I have sine and cosine. I need to know what the theta is. So I can say that the tangent of the theta, which is the sine over cosine, is going to be equal to the MA divided by the MG. And by simplifying, because what I can do here is I can remove these two from both ends. So I will say that the tan of theta is equal to the mg divided by the MA, or I can even simplify that. So the theta is going to be equal to the tangent inverse of the A divided by G. So do you have any question about the two questions that we covered earlier, or just make them for you straightforward? Oh, we have something in the chat. I didn't notice that, sorry. Yeah, 46. Yeah, we came to this conclusion. Sorry, I hadn't read that earlier. I know I'm quite slow here. Okay, so all good for these questions? Did I lost your yeah, okay. Yeah, so let's continue with further questions. And again, it's going to be almost with the same level. I don't want to take you to a very high level. And it's about this truck. The truck has a drop gate here in the back. And this drop gate connected to the cable AB. This cable AB will be cut suddenly, and then we're going to have the things to rotate around the point C. So the drop gate at the end of the trailer has a mass of 1.25 megagram. Just remember that the megagram means millions of grams. So you divide by 10 up to power 3, you will find how many kilograms are. And the mass center at the point G. If it's going to be supported by the cable AB and the hinge at C, then what will be the tension in the cable when the truck begins to accelerate at 5 meters per second squared? Also, what are the horizontal and the vertical components of the reaction at the hinge C? So, well, actually, there's no rotation. We just need to know what are the reaction at the point C and what will be the cable A, B tension. So mainly we're going to use the same equation, but we start first with the free body diagram. It's obvious we're going to have reaction CX and the CY. And in this scenario, actually, I found that he used the axis is to be, this is the X and this is the Y. He didn't use it the normal way. I mean, it's not that way, but it's up to you. At the end, you're going to find the same answers. So, yep, we have the mass at the center going downward. We have the tension in the point A going by 30 degrees to the left, and we have the reaction Cx and the Cy at the point A vertical and horizontal components. The mass is 1,250 kilogram multiplied by 9.81, and it's going to be 12,262.5. Now the unknowns are going to be the T, the Cx, and the Cy in the free body diagram. In the kinetic diagram, we know the mass, and we know the acceleration is 5 meter per second square. So we can simply find what will be the horizontal component of the force in the kinetic diagram. We don't have any vertical one because the truck is not going up and down. So once again, the three equations we use are going to be those. And now, without going actually to the other side, let's see what we can have. Okay, so here, for the x-axis, for example, we have the t multiplied by cosine of 30. We have the Cx on the opposite direction. That's it. And on the other side is going to be 12,250. So we can find a relation between the T and the Cx. We go into the y direction. In the y direction, we have the vertical components of the T and is negative. And we have the weight is negative. And we have the Cy is positive. On the other side, it's equal to 0. Now we can find the value for the Cx in terms of T. So I couldn't find anything yet. So I would like to know what will be unknown. So I can do the moment around the point C, which is going to be equal to the weight multiplied by that distance, which is the half of the length multiplied, or 1.5 multiplied by the sine of that angle. Okay, sine of this angle here. And actually very easy to find this one. And else we going to have, okay, so this force multiply the vertical force and the horizontal force. Yep. So then the vertical force of the T multiplied by that distance. Now both are going to go to the clockwise direction, and thus is going to be a negative value. Now the horizontal component of the T to be multiplied by that height, and this will be a positive value. Now we go into the kinetic diagram. It's going to be the 1,250 times 5 multiplied by that height, and it's going to be positive. Then I can solve for the T. I will find the T, go to the equation we got for the relation between the Fy and the Magy to find the value for the Cy, and for the Fx, I will find the value for the Cx. So that's what I just mentioned. That was the moment equation I started first. And you can see in the moment equation, only T is unknown, so I can solve for the T. Okay. Okay. Now we're going to go to the forces to the x-axis. I'll solve for the Cx. Go to the forces to the y-axis. I will solve for the Cy. Now, in this question, I didn't actually put any answer because that's something we've done earlier. I said that this cylinder is moving without any slipping. And we want to know what will be the acceleration of the center of the cylinder. Okay, so in this scenario, we can find the p-value if we know what the mass is and what the value of the r by saying that this p is given to us. We know this one is not slipping, so we can simply find the centers here. And we said that the acceleration on this point is going to be equal to the alpha multiplied by the r. Or the velocity, we can actually find it as well, because it's going to be equal to well, that's the acceleration, if you want to know the answer. Okay, and once again, I'm going to update you with this one later. I found another question which is similar to the one we have in the case of the quiz. It's not exactly the same, but it's about a trolley to be pulled with a certain value for the P. It's going to be having a certain mass, certain value for the P. And we need to remind what will be the reaction at both wheels at the A and B. And also what will be the acceleration of the cart, and the mass center is given at the point G. So do the free body diagram. It's something similar to the one we had for the race car. Okay, we know the distance, the point G, the height of the point G, the weight is going downward, the acceleration is unknown. This force can have two components. We're going to be a vertical and horizontal. Okay, and we can come to the answer. So you can see here that actually, well, actually this should be changed. I'm sure that this is not the correct moment around the point C. It's not around the point C. If I was you, I'll take the moment around the point B, so I can eliminate the MB. We'll see that very soon. Oh, sorry, I didn't put the answer. I just show you the example. So yeah,
Sir,
this one is to
here,
be around the point B. Yeah, I can hear you. Yep.
sir, it's a very dumb question, but when you mean
There's no dumb question.
MB MBK, do you mean the moment in the K axis?
Around the point B.
Around the point B in the K axis, right?
Yep. Well, whatever, because what we need to do, if I would like to take the moment around this point, is going to
Yeah.
be the NA multiplied by 0.5, right?
Yeah. Yeah.
The weight multiplied by 0.2. Now this one is going to be clockwise. This will be a counterclockwise, right?
Yes.
And also, what we have here is that this force is going to have two components. The horizontal one is going to be multiplied by 0.4, and it's going to be counterclockwise. And the vertical one is going to be multiplied by the 0.5 plus 0.0 meters, and this will be to the clockwise. Okay, and thus we are going to have the kinetic diagram, the free body diagram moment. In the kinetic diagram, what do we have? We have the MA multiplied by 0.3. That's what we have for the moment for this direction around the point B. Force to the x-axis first. It can help a lot because the force axis we have is that P is known. That's one. Okay, and this one. That's the free body diagram. It's going to be the P cosine 30. And this will be equal to the mass multiplied by the acceleration A on the kinetic diagram, which is the mass is known, so we can find the acceleration. Done. To the y-axis, let me clean that. It became too messy. And the y-axis, we have the weight going down, negative, the 300 sine of 30, and it's going to be NA, NB. So this is positive, this is positive, and this is positive, and this is negative. So we can find the NA in terms of the NB. Now, we found the A from here, we found the NB in terms of the NA from here, and then we can use the moment around the point B to find what will be the value of the NA. Then we're going to substitute it to the equation we got from this relation to find the value for the NB. It's not that hard. Just think about it as I did it. You find this one to find the value for the acceleration. So you solve half of the problem. From here, you're going to find the value for the MA as a function of NB. Now here, do the moment around the point B. you will find the NA. And then substitute in this equation, you will find the MB. Okay, so it's not that hard. I think that will be the other one is going to be that's the question we have here. I'm only going to do the part A, and you will need to do the part B yourself. The cylinder with a rod has a mass of 5 kilograms. The code A will be cut suddenly. Well, actually, I'm rushing because we passed the time we have in 1 hour now instead of 30 minutes. Yeah, so the rod is going to be cut suddenly and the bar will start to fall down. So we need to know when the rod is still horizontal, what will be the value of the reaction at the point O. So in this scenario, the omega is 0. The AGT, or the acceleration at the point G, the vertical one, or which is tangential, is going to be equal to the alpha multiplied by the distance from the O to G, which is 0.2. Now, how we found that as a 0.2, because the whole length is 600. That means it's sitting something at the point. Wait a second. It shouldn't be 0.2. That should be 0.3. Anyway, we'll see that. The AGN is going to be equal to the omega multiplied by the R. So the omega is 0, so the R is going to be 0. 0.6, 0.3. Oh, sorry, yeah. We got the distance to be 0.2 from here to here, because the total length is 800, and this make that the centroid to be at 400 on the end, and that means it's going to be at 200 from the point O. That's how we got the value 4.2. So this one is actually alpha R, and this is the omega square R, because the omega is 0 at the first state, so this will be equal to 0. Now, as usual, we're going to try to find the moment around the point O. So in the free body diagram, it's going to be equal to the weight multiplied by 0.2, and this will be a negative direction. And the kinetic diagram is going to be the IG alpha, or the IO alpha, actually. It's IO alpha. So that's what we got in the free body diagram. It's obvious, this force multiplied by that distance. And the other side, IO alpha. So we calculate the IG, which is 1/12, 5, the mass, multiplied by 0.8 square, the length square, plus the 5 multiplied by 0.2 square, or the mass multiplied by that distance square, multiplied by the alpha. So now, what the only unknown we have here is going to be the alpha. So we can solve for the alpha, and it's going to be 21.02 radian per second square. That's it. If I find the alpha, it's going to be much easier for me to find the other reactions. So, for example, I will take the normal direction, which is going to be, in that case, the horizontal one. That's the normal. The free body diagram, normal forces are the OX. And the kinetic diagram is going to be equal to the A multiplied by the AN, the mass multiplied by the AN. So the AN, or the AG normal, is 0, so I can say that the reaction is going to be equal to 0 to the x-axis. Then I will go to the tangential one. This force is going to be equal to mass multiplied by the GT. GT now is known because we know the alpha, so I can find this value. On this direction is going to be the OY minus the weight. So I can solve for the value for the OY. And it's going to be equal to 28 Newton. If I would like to find the resultant, I just need to add the 0 square plus 28 square under square root and I will find the answer for that. Okay, so I shall stop at this point. I don't think that more to come. And again, if you have any questions, you can simply just come back to me, and again, to be more than happy to answer further questions. So this video and the other 3 slides that we had a look at, the 4, 5, and 6 weeks, are already available for you. All the examples has a video available for you. This video, actually, after we finish, is going to go to YouTube, so you can come back to it and have a look about what we covered here. Okay, so thank you very much for your attending, and hopefully next week I'm going to be prepared to the quiz question before I come into the class. Okay,
Thank you,
thank
sir.
you very much, and sorry
Thank
if
you.
I was too disturbing. It's Friday.